Okay, so let me start by just doing a brief summary or recap of, because so that we don't get lost of what we are doing. So remember in my first lecture I was talking about average versus extreme. And I gave the example that, for example, if you take the daily temperature, hourly temperature per day in Bangalore city, and if you average over 24 hours, and you look at the histogram over 30 days, that will be typically different than if you do, for example, for each day you look at the maximum temperature, and then for each day you have a number, and then you draw the histogram. So the distribution of the average is different from the distribution of the extreme. And what we saw yesterday's lecture is essentially a manifestation of that. And let me just recap that thing. So, okay, I'll use a slightly, since I was talking about two different models. So one is, IID variables, and the second one is the random walk. Now, for the random walk problem, the IID variables are the noise increments, eta 1, eta 2, eta 3. Whereas for the IID model, they are the actual xi's. Okay? So let me just say that suppose that you have n IID variables, each drawn from some PDF f of eta, and this f of eta is normalized to unity. And let's also assume that its first and second moment exists. So usually we are considering the symmetric distribution where the first moment is 0, but you can do it for general case when this is asymmetric distribution such that the mean exists. And we also assume that the second moment exists. So these are finite. So therefore, the variance of one particular element is just mu2 minus mu1 square. So this is also finite. But this does not mean that they are Gaussian distribution. They can be anything. It's just only assumption is the first and second moment exists. Okay? So they can be distributed any way you like. And so average means the sample average. That means in a given sample, so that means I denote by x bar. So this is, sorry, you just take n of them and you divide by n. So this is the definition of an average, right? So for example, this could be the temperature at each hour, and then I have 24 such values, and I divide by 24, that will be the average temperature in a given day. But of course, this guy is going to fluctuate from day to day because these are random variables, so therefore x bar is also a random variable. And we can ask what is the distribution of x bar? So distribution of x bar is very easy to compute because this is a random variable, so this bar means sample average basically, you just divide by n. And now I take a statistical average over the etas. So then because each eta average is mu1, so therefore this is just 1 over n times mu1. So n cancels, so you have mu1. Okay? And if I calculate therefore the variance, that means I subtract, I look at the fluctuation from this average value. So that will be just 1 over n times summation I equal to 1 to n, eta I minus mu1. So it's just fluctuation of each variable. And so if I now calculate the variance of this, which is defined as this fluctuation from this average, and you square it, and then you take a statistical average of that. So this will be 1 over n square but the etas are uncorrelated IID variables, and therefore this is just 1 over n squared times n. So only diagonal elements will matter. Off diagonal elements will be 0 identically, and there are n of them. So n times the variance of eta 1, let's say minus mu 1 square average. But eta 1 minus mu 1 square average is just sigma squared. So therefore you have sigma square over n. So this is the mean, this is the variance, and what is the distribution? So remember that last time, you see that if you think of this as a noise increments, then this, up to a factor of n, this x bar is precisely the position of a random walker up to after n steps, right? So this sum here and we showed in the last lecture that this sum or position of a random walker after n steps by central limit theorem is, if these things are valid, it goes to a central limit theorem, which means that x bar will converge in the large n limit to a Gaussian distribution, and therefore, and for Gaussian distribution we just need the mean and variance. So therefore you can write this as 1 over square root of 2 pi times the variance, and variance is just sigma square over n times exponential minus mean is just mu 1 so you see this variance actually goes like sigma square over n. When n is very large, the variance goes to 0 almost, because that's why you take more and more averages when you do numerical simulations, so that the fluctuations goes to 0. Okay, so you can determine it with this. So this is the central limit theorem, and this you can see that you can write it this way. Where you can read off an and bn. So clearly an, so these are just some constant. An is independent of n, it's just mu 1 from this. Bn is just sigma by square root of n. So it's this guy here, this guy there. But the scaling function and this is universal in the sense it does not depend on the details of the f of eta. It only depends on the just the first two moments. Okay. So, and this is what you see. The interpretation of an is that this is just a mean. So if I plot this function, so its mean is at mu 1 or an if you like, and its Gaussian distribution around this mean with a width which is measured by this bn, and that goes like sigma by root n. So as n goes to infinity, this width decreases, it becomes narrow and narrow. Eventually, of course, it goes to a delta function centered around the mean. But for finite but large n, you can always write it in the scaling form. So the interpretation of an and bn in this example is very clear. So they are mean and this width. But this function itself is universal in the sense that it does not depend on the other details of f eta. And this is the statement of the central limit theorem, that the scaled distribution is always given by Gaussian as long as the mean and the variance is finite. Okay? So this is the statement of average of n IID variables. And now then we discuss the extremes. In particular, the maximum. So we looked at Sx max equal to, so again IID variables. Okay. So x bar was just this definition, sum divided by n, and x max is just the maximum of these IID variables. Okay. And what I showed in the last lecture, that if f eta, I was in the last lecture I was calling it p of x, but here I wanted to say it in terms of eta because the eta is common to both models. Eta is noise in the random walk model, whereas eta is actual variable xi itself in the IID model. So if f of eta decays faster than power law and unbounded, for example, f of eta could be, for large eta, could decay like eta to the power delta, where delta is positive. For example, it could be Gaussian, it could be exponential, etc., etc. Okay? So if f of eta decays faster than these things, then what we show is that p of x max comma n, the PDF of the maximum. So it also has a similar scaling form as average, namely for large n limit. So this is, of course, the large n limit. It goes into this form, which I call Gumbel distribution. And just as in the case of averages, these an and bn are scale factors which depend on the details of how it behaves. For example, we saw that for this particular example, I showed in the class that this should be log n to the power 1 over delta. We saw how to determine an and bn. So okay, so they of course depend on the details of this PDF, but this function, scaling function, this is a universal function. And it's called the Gumbel PDF. Okay, so that means same thing exactly like this. If I plot the p of x max now, comma n versus x max, it will be picked around this an. But the shape of this function is very different, very asymmetric here, something like that. And again, this width is this bn, okay? And the scaling function, if you, for large n, if you scale it, your x and y axis, center it and scale it, they will all collapse onto the same universal function, which is this Gumbel PDF. Okay? So what you see is that these two functions, one is Gaussian, and the other is Gumbel. So they are actually very different from each other, right? So this is a symmetric distribution around mu1 with the width of bn. Of course, the n bn's are very different. But so you should look at always the scaled function. The scaled function itself, in one case is symmetric Gaussian, and in the other case, it's actually is very different. It behaves like this asymmetric function. Okay? And this is a sort of nice experiment that all of us can do. Just take the data from the internet of the hourly temperature, let's say, of some city like Bangalore, and just do the histogram of average. That is, you divide by 24, Just take the hourly temperature, and you do the same thing for the X max, and you will see that their behavior will be very different. In one case, it will be more or less Gaussian, like this, central limit theorem, provided, of course, they are uncorrelated. And in fact, this you can use as a test to know whether your underlying random variables are uncorrelated or not. So you should see that X max, average value of X bar should be Gaussian and X max should have a Gumbel, provided, they are independent and that A theta decays faster than power law. But otherwise, you will see that, they'll be different, okay? So that means they might be correlated actually, okay? So this is the sort of basic recap of what we did yesterday. So this is just wanted to make clear these things. So for the extremes, we studied the case, so this is, I call it case 1, and I was denoting in my last class this function, I mean the cumulative function, so this was just f1 prime of z. I was calling this guy as f1 prime z. 1 was for Gumbel, and we'll see why. Yeah. Yes. Right. Yeah, this is because you are looking at the maximum. Because each data, in some sense, you are biasing towards more than the average, right? So because you are looking at the picking up the maximum from each sample. So if you are done the minimum, then it will be the other side, basically. Okay. So that's yeah, I'm not doing the minimum, but minimum is exactly same. If you have eta 1, eta 2, eta 3, you just take the minus of eta 1 and then look for the maximum of that. That will be the minimum distribution. And you see that immediately it gets to the other side, basically.
So there is no physical minimum, you're not attributed to the fact that if I take IOD variables
Right.
that are essentially uncorrelated and have these properties, are more likely than not have larger X max values than, is that something which we should infer from this? What I'm saying is I'm looking at temperature data.
Right.
I'm just asking the naive question, how does
The maximum distribution look like, right?
Yeah, and then if this is the universal distribution,
Right, right.
then in some sense I'm saying you're more likely to have higher maximum temperature.
No, it says that, okay, I mean, if you do your experiment, and if you, let's say you just draw the histogram, okay? Draw the histogram, and if you see that, it doesn't match with Gumbel, okay? Then you know that your basic assumption that they were IID variables was wrong. Because if they were IID, then you have to get Gumbel. So this is a sort of, you can use this as a test to know if the underlying variables are uncorrelated or not. Yeah.
But it doesn't have a predictive power in terms of whether the maximum temperature is more likely to be higher.
Yeah. So it just says it just says maximum temperature itself is a random variable, and it has some distribution, but it doesn't tell you exactly what value it has because it's a random variable. It doesn't have a fixed value basically, right? Because maximum will again, I mean, it will vary from day to day maximum temperature, so it doesn't have a fixed value basically, right? So it's
That I understand.
yeah.
What I'm saying is if I've been given the PDF of the
Right,
maximum,
right.
then I choose, then I'm more likely to choose from the fact tail for the maximum.
Sure. I mean, you will.
So I'm more
Yeah.
likely to have higher values of mine.
Absolutely, higher than the mean. Yes,
Higher
higher than the mean. Absolutely, yes, that's true.
More likely than that your things are lower, right? As maximum. Because if you pick a very large maximum value, they may be likely there, but then it's much more likely that it is maximum because it's a hard mode, right? Just like
Yeah.
that. So
Exactly.
then
Yeah.
it makes sense that but if your data is squeezed into that, then it's yes and yes.
Yeah. Yeah. Okay, so there, I looked at case 1 when A theta has this, very narrow tail. It's decaying very fast with increasing eta, so faster than any power law. So next question that you can ask, this is number 2, that what if A theta has a power law decay? for large eta. Let's say something like alpha. Where alpha is positive. I write alpha plus 1 because this guy has to be normalized. Okay, so alpha must be positive in order for it to be normalized. But you know, its first moment or second moment may or may not exist depending on the value of alpha. But let's just take this f of eta, and we want to estimate exactly the same thing. What's the probability distribution of x max of n? Okay. So remember how we did for the other case. So we looked at this object, cumulative distribution of x max. So probability that the x max is less than or equal to x, which is the same as the probability that each of them is less than x. So therefore, okay, and then we wrote this as 1 minus x to infinity using normalization of f eta. And then we say that, okay, when n is large, I mean, if I want to make this guy as order 1, this x must be large so that this quantity is small. And then I can just write down, expand this, I mean, I can write down, okay, this I can write down exactly as n log 1 minus x to infinity f eta d eta. And then I just take the large n limit, and in large n limit, the leading term is just f eta d eta. I neglect the other terms because they are subleading corrections. And so if I have to take the n going to infinity limit, if I don't do anything to x, it just goes to 0. So to get something interesting, I have to also send x to be large so that this quantity is small, such that the product, big quantity and a small quantity, remains of order 1. Okay? So that gives me the estimate of this an, as I said. So this, and this has the physical implication because this just says, you know, this is just the fraction of etas which are bigger than an, but since an is roughly the maximum value, it must be 1 over n, so that's how you determine this an. Okay? But anyway, this is the formula basically, and you need to analyze this. Okay, so let's just use this form now. Since x is large, I can just use this form by e to the power minus n. Okay, let's call it some amplitude a here. So I just put 1 over eta to the power alpha plus 1 and just do the integration x to infinity. So that gives me x to the power minus alpha divided by alpha. Okay. So which I can write as x by bn to the power minus alpha, where I just rewrite this. Just absorb this in bn and write it this way. Okay? So therefore, what you see is that again, this object q max equal to this, I can again write this in a scaling form in the large n limit. Call it f2. How is this of this type? So this immediately indicates that an equal to 0 and bn is just this number, right? So and my scaling function f2 of z for z bigger than equal to 0 and 0 for z negative. I mean, z cannot be negative, of course, because z is always positive here. So therefore, this scaling function, so again it is the same scaling form, f2 of x minus an by bn. Of course, an and bn are non-universal. They depend on the tails. But again, for any power law, you know, it will always, the scaling function will be always universal. So this f2z, if you plot this is a cumulative distribution, so it goes, so it's 0 here and, sorry, it's when z goes to, yeah, it's sort of, you know, it's 0 here and then it sort of increases like this and approaches to 1. So as z goes to infinity, it must go to 1 because it's a cumulative distribution, right? When x max goes to infinity, probability that x goes to infinity less than infinity is definitely 1. And so its derivative, so therefore the p max, the PDF of the maximum, is just the derivative del x so that has the scaling form if I take a derivative. Where this f2 prime of z, so f2z is this, if I take a derivative of that, so this just becomes and of course z is positive, theta of z. For z negative, it's 0 identically. So if I plot this function now, this PDF, the scaled PDF, yeah? Tell me.
In the larger limit, you get e to the minus n of the logarithm.
Right.
Then how do you get, what is this as? E to the minus n ax to the minus alpha upon x. How do you get that?
Let me see, did I make a mistake here? This is 1 over x to the power alpha, right? Yeah, so this is fine.
No, why do you get that? From there you.
Oh, from here, right? If you just substitute a,
Sorry, okay.
you just integrate basically. Yeah. You just, I didn't do this step. I mean, you just put these things and then you just integrate because x is large, right? So therefore, this is the leading behavior. And yeah.
So for large it's larger.
Yeah. Always you have to take, see, in order to get a scaling limit, because it's a function of two variables, right? So you have to send both of them in some way such that some combination gets fixed basically. So that's the idea. So okay. So if I plot this scaling function now, so this looks like it goes to 0 as z goes to 0, and it sort of picks up, and then it has a very slow tail. And here for large z, it decays like 1 over z to the power alpha plus 1, power law decay. Okay. And here it has an essential singularity as z goes to 0. So this distribution is f2 prime z. So this is called the Fréchet distribution. He was a French mathematician from the French statistician or mathematician, whatever. Okay. So we have seen there is a Gumbel class when this function, when the tail, so everything depends on the tail of this f of eta. If f of eta decays faster than power law, then it goes to the Gumbel class. If it decays as a power law, then it goes to this Fréchet class. You see the Fréchet distribution is very different from the Gumbel also. Okay? So again, it has a peak. And so if you plot the Bayer distribution, an is 0, so it is more like a scaling distribution. It's not, I mean, an is basically, there's no center, mean or something. So it's just a scaled value, basically, some function of x over bn. Okay? So this is the Fréchet, and then there's third category, which I didn't want to remove this. Okay, but I'll remove that, I'll write it again. So far we have, think of a theta tail. So it's decaying exponentially or Gaussian, etc. very fast. That's one class. Then it decays slower than exponential, which is like a power law, decaying very slowly. And now I go on the other side. That is when it decays much faster than exponential. For example, if it is a bounded distribution. So for instance, I could take f eta to be a uniform distribution. Yeah. Sorry? This guy, you have to take a derivative and put z equal to 0. No, it's not an n-dependent number. It's just an odd number of order 1, basically. So for example, if I take uniform distribution of f eta, so that means it's a flat distribution. Let's say 0 to 1. Okay? So this is even faster than exponential because it has a finite upper limit support, right? Beyond that, it's identically 0. So in some sense, it's decaying very fast. Okay? So one side, so you have the exponential or Gaussian, etc. Slower than tail is a power law tail, that's a Frechet. Then you have the Gumbel in between. And then now we are on the opposite side when it's decaying even faster than exponential, if you like, with a finite upper limit. Okay? So then what happens? So again, so we have the basic formula always, is this formula here. Yeah, of course. That as I explained, because it's a maximum, so it has a higher tail than lower tail, basically. Okay. So this, again, in the large n limit, the approximate formula we said, this is very general. But now your f eta is just finishing here. It's a constant. So f eta is just uniform distribution, means is 1 if x is in 0, 1 and is 0 outside. So therefore, this integral just becomes x to 1 f eta deta. So first thing you notice that clearly x max itself cannot be bigger than 1 because each of the variables, I mean you are choosing each variable from this uniform distribution, so all of them are less than 1. So clearly x max cannot be bigger than 1. Okay? So x max is necessarily also lies in the interval 0, 1. Okay? And therefore you can see that from here. So if f eta is 1, so this x is between 0 and 1. So this will be n times 1 minus x. Right? Because f eta is 1, so the integral is n times 1 minus x. But then this one I can also write as in the same form. You see there's everywhere for average, for maximum, I'm always writing this scaling form. And I'm going to find out what is an and bn. So clearly from this example, what you see is that the an is just 1 and bn is 1 over n, and the scaling function f3z is e to the power minus mod z for z this thing, and 1 if. Is this clear? Just check. I mean, z is, an is 1 and bn is 1 over n. So therefore, z, I mean, in this, by z, I mean this guy, x minus an over bn, is just x minus 1 times n, right? And what you have is e to the power minus n 1 minus x. So it's just the absolute, because x is less than 1, so z is negative. And therefore, it is e to the power minus absolute value of z for z negative. And for z positive, as I said, x max cannot be bigger than 1. So that means, this guy is 0 identical, which means that this is 1. Okay? So f3's function is 1. Okay? So this is for this particular case of uniform distribution. But you can do a more general case. So take any distribution whose upper tail is bounded, okay, at A. So that means the distribution f of eta looks like uniform is just one example, but it could be anything, any shape, but it has a fixed upper support A. Okay, nothing beyond that, which means the maximum cannot exceed this value A. So this necessarily means x max certainly less than equal to A, supported over this. Okay, and suppose that the f of eta. So what matters is again tail of this function, and here by tail I mean the behavior near the upper support basically, because in this integral you will have x to that upper support. So suppose that near this upper support here in this regime, f eta has very generically some gamma minus 1 where gamma is positive. It doesn't have to go to 0, it can diverge also, but integrable divergence. So suppose that this is the local behavior here, this upper support. Okay? And again, I'm going to use this formula here. So and so f eta I have to just put b times a minus eta. So just looking at locally, zooming in this regime, because most likely x max is concentrated around this regime with some width here, and we can figure it out from there. So if I just do this integral, it's trivial. So what you find is that e to the power minus n b over gamma a minus x to the power gamma. And again, this guy I can write in my favorite scaling form. Where you can read off what is an. An is clearly A, the upper limit itself. So maximum is most likely will be close to A, but then with some fluctuation around that, and that fluctuation is encoded in this Bn, and this Bn is just gamma over Nb. Okay. And then this function f3 of z So uniform case that I worked out as an example, so that corresponds to just gamma equal to 1, yes. And so you see generally if you have any bounded distribution like this, then the corresponding scaling function, so no matter again this an and bn will depend on the details of how this f of eta behaves, but the distribution of the maximum, this is the cumulative distribution, is always given by this form, which means that if I take the derivative of this, so derivative will be just gamma, let's see, so therefore, so what you see is that so the PDF of the maximum in this third class which is the derivative of q with respect to x, which means 1 over bn, it converges to this in the Largen limit into the scaling function f3 prime this f3 prime, this scaling function, is given by this basically. So it has support only on the negative side and 0 otherwise. So this means if I plot the scaling function, it has support only on the negative side. So it goes like this. Here it decays exponential minus mod z to the power gamma, and here it's identically 0. So you see that here in this case it's sort of, maximum is, it cannot be bigger than 0, z be bigger than 0, that means x must be less than equal to an, okay? Because this is bounded, so as I said, maximum cannot be bigger than this. So maximum is, it's supported on the left of A, and on the left of A, it has this distribution. So that means most likely value of the maximum will be some z, which is of order 1 on the negative side. Okay? Negative because it has to be less than A. The way we are written down here, the argument must be negative. X cannot be bigger than an. So this argument must be negative for it to be non-zero. Okay? So this is this distribution is this function is called the Weibull distribution. So just to say it again, because in physics it's very important to understand scaling, because this is the first thing that you have to know. This is not just statistical physics. Particle physics or cosmology, astrophysics, everywhere. Scaling is very important. Okay. So and the universality. So the idea is that, if I look at a particular object, like for example, if I measure the specific heat of a material in my lab, as a function of temperature or something, then you'll see copper will give one behavior, nickel will give another behavior, or some other metal will give some other. Is it interesting? No, it's not, because each material has its own properties, right? But if you scale appropriately, they're all described by the same function. They all belong to the same family, and this is the beauty of universality. So that's why it's not that I have to study each material separately. If I know that there is some underlying universality, then they're all described by the same family. So you've identified the reason for that they belong to the same family. So this is the concept of universality. And here what you see in this example, similar ideas, that is that even though the actual maximum distribution, for example, if you plot in, the temperature distribution, maximum temperature distribution in Bangalore, then you plot for another city like Calcutta or New Delhi or Bombay or something, they might all be very different from each other, okay? But if you scale it appropriately, that means you shift by some an, which may be different in Bangalore and Bombay and Calcutta, and bn might be also different, but if you subtract of those mean and scale factor, they will all be described by the same function. Okay? So this is the universality. Okay? And so we have seen 3 universal functions, which is Gumbel, Frechet, and Weibull. Okay, so let me now summarize these things. So extreme value statistics for the IID model, where my input is this f of eta. So remember that the joint distribution of these etas, because they are IID, so it's just a product of f of eta I. So my input is f of eta. You have given me the f of eta, and I want to know what is the distribution of the x max. Where x max is and the statement what we showed, we studied 3 classes of f eta. So first thing is that everything depends for large n. So for finite n, of course, there is no universality, and we have an exact formula. So this object is just, as you saw, that this is just n times fx times f eta x. So this is the general formula, because we looked at the cumulative. Cumulative was this guy to the power n, and when you take a derivative, the n fx comes out, and this has a physical meaning that maximum out of n guys, suppose that one particular guy is maximum, which happens with f of x, then all the other guys have to be less than x, but that maximum can be any one of the n of them, and therefore you have this is the PDF of x max. So this is a general formula. But this formula, of course, is you don't see immediately, obviously, from it any universality. So to check the universality, to search for universality, you have to look for large n behavior, okay? Just like in central limit theorem for the average. And in the large n limit, what we saw that this PDF typically converges in the large n limit to some function where this an and bn are non-universal scale factors, which depends on the details of the tails of fx. But the scaling function f rho of z can be only of 3 types: f1 of z, f2 of z, and f3 of z. I mean, these 3 cases we discussed. So this is Gumbel. And this happens if f of eta has a faster than power law tail. This is given by the Frechet form. If f of eta has a power law tail, and is given by Weibull form if f of eta is bounded above. Okay. So the question is that, are there other classes, or is it only these 3? Okay. And so here I will not, of course, prove it, but it was actually proved by the mathematician Nedenko in 1943, long back. So what he proved is that for the IID model, okay, no matter what f eta is, okay, that the distribution of the maximum of f eta will go to either one of these fixed points depending on the tail of a theta. Okay? So the details might be very different, whatever, but these are the only three possibilities. Okay? So, in other words, you can draw like in condensed matter physics, you always do, statistical physics, you always do. There are basically, if you think of this all as a functional space, all the space of a theta normalized, then, basically there are three fixed points, if you like. So this is the Gumbel fixed point, the Fréchet fixed point, and this is the Weigel fixed point. So each of them has their own catchment areas. Okay? So all possible functions that flow under large n, the distribution of the maximum, flow into the Gumbel fixed point. And this is the condition for that is precisely this condition. That is, a theta should be faster than, fall off faster than power law. So the whole function space gets divided into three domains of attraction. Then this guy has his own domain of attraction, where a theta has a power law tail. And this is all functions that are bounded above. They flow into this fixed point here. Okay? And these are the only three possible fixed points. Okay? So this is very nice. So it says that, it's a beautiful universal theorem. So, I mean, you imagine that your infinite number of a theta is possible. You can think of any possible positive PDF function. But no matter what you choose, you will essentially, in the large n limit, there is universality. And this universality has basically three fixed points, and it will flow into one of these three fixed points. Okay? So that's a very powerful theorem. Huh?
But in the upper bound and the Weigel towards infinity, then it goes to either Gumbel or towards...
Yeah, if you take the upper bound to be unbounded, then of course, but okay, I mean, sometimes, for example, I mean, you can have a, this is not exactly strictly the theorem. I mean, you can have a, for example, something which is, let's say upper bound is somewhere there, but is actually becoming zero, as an essential singularity or something much before that, okay. Then, this is effectively like the Gumbel class, because, in some sense, the upper limit has gone to infinity. So this will be, I mean, you can, for all practical purposes, you can think of it as unbounded, okay. So, but basically you cannot, get out of these three classes. It will be one of them, basically. And this is a very powerful result because, it just says that it's quite beautiful, right? I mean, instead of like, thinking of specific hit of 10,000 materials, you have only three possible curves. I mean, so this is the beauty of universality for the IID model. And in fact, I mean, the another thing that you see the power of this universality is, as I mentioned, so now that if you have correlated variables, so that it's not no longer IID, okay? So let's say eta 1s, eta n's, they are now correlated. But let's say they are weakly correlated. So what this means, as I said, that there is a finite correlation length. This means there is a finite psi, which is much, much less than the system size n. So the picture I was drawing, remember, so you have my time series entries. I call it now etas, but okay, I mean, there I was calling it as x size, but doesn't matter. So I have n entries, and since they are correlated over a length scale psi here, so I divide the system into blocks of correlation length psi. So this is exactly like the real space and renormalization group calculation. So I will have n over psi blocks, and so from each block I just look at I compute the local maximum of each block. Okay, let's call them y1, block 1 maximum. This is y2 from second block, and ym. Okay, so this block maximum, they are essentially uncorrelated IID variables. So I don't know what is f of yi. I don't know how they are distributed, because to compute that you need to know how the maximum of very strongly correlated variables behave, which I don't have knowledge. Okay, but I know that y1, y2, y3, ym, they are uncorrelated because they are across the correlation length. They are correlated, only these guys are correlated up to this. Okay, so they're effectively uncorrelated, and therefore all I know is that no matter what the individual distribution f of y is, which I don't know how to calculate, but I know that under this universality theorem, because the block maximums are themselves uncorrelated, I will flow to one of the three fixed points. So for weakly correlated variables, if you, for example, just do a simulation over one block and you find out whether it has an exponential tail or a Gaussian tail or power law tail, if it is a power law tail, you immediately know that the maximum, global maximum for these weakly correlated variables will go to the Gumbel, Fresher, or Weibull class. Okay, I don't need to know really the details of the block maximum. Okay? So that in that sense, the weakly correlated variables is essentially flows back into the uncorrelated variables under these renormalization arguments. Okay? But of course, for strongly correlated variables, when this correlation length is much, much bigger than n, an example of that we are discussing is the random walk case. So there, of course, I mean, I cannot use this argument, okay? So there, I mean, you don't expect any of these three universality classes to appear, and it will be completely different classes for correlated variables. And one of the problems now, I mean, open problems in this field, is to, what can we say about strongly correlated variables? I mean, are there any similar universality classes? Can I classify them? Nobody knows the answer. So at this stage, the situation is that, okay, I mean, you have to solve individual models to get as much insights as you can, but there is no general theory like this for the distributions of the correlated, strongly correlated variables, maximum distribution of that, okay? So, so that's why, I'm just looking at one particular example of this random walk case for which we can actually say quite a few things exactly. And this is one example of a strongly correlated variable, okay? And so what we do next is to actually compute the distribution of maximum for the random walk case, where we know that it is strongly correlated. And we'll see that it will be very different from any of the three distributions. Okay. You want to put a break now? Yeah. So one thing I did not do, of course, I mean, you can, same thing, I mean, you should take it as an exercise. You can carry out the similar analysis for minimum, for example. I mean, I looked at the maximum. The minimum will be very similar. So for the minimum, you should look at the cumulative distribution. So this is the probability that x min, where x min is defined as minimum of this eta 1, eta 2, eta 3, eta n. So what's the probability that the minimum is bigger? In the maximum case, it should be less than, minimum case, it should be bigger than x. That's how you define. Because this event, if the minimum is bigger than x, that means each of them is bigger than x. And so, essentially, again, you have this general formula. Yeah, okay, I mean, eta in terms of eta, so. So it should be bigger than x, so it will be x to infinity. For the maximum, it was minus infinity to x. For the minimum, it will be x to infinity. And again, for IID variables, if they are product, so you just have this formula here. So integral from x to infinity, f eta d eta to the power n. And again, you can repeat the same exercise I did it for the maximum. There it was minus infinity to x, and here it's x to infinity. And you have to see how, as you take n to be large, how you should scale x in order that this is something of order 1. And so this is the minimum, and you can also ask for the joint distribution of maximum and minimum. So you should look for then what is the probability that x max, let's say, is bigger than x, and x min is less than equal to x, sorry. And x min is bigger than equal to y. If you know this joint distribution, then by taking derivative with respect to x and y, you can find the joint PDF of x max and x min. And what is this object? This means x max is less than x and x min is bigger than y. That means each of the variables must lie between x and y. And therefore, this is just the formula again. And again, you can try to work out exactly the way I did it. That is, when large n limit, how should you scale x and y such that it has some kind of scaling form? And you can find out what is the, in fact, what happens in the large n limit is that the x max and x min get uncorrelated, and but their joint distribution is given by the product of the individual distributions, basically. But so you can work it out many different things. I mean, you can calculate the distribution of x max minus x min, which is a span, how much spread basically of your data set has. So all these things you can actually exactly compute and analyze in the large n limit, but I won't do all these details. You can find in the book if you like. Okay. So in the next half an hour, next half, I'll do just the maximum for the random walk case, just to understand, to see how the correlations affect this picture of universal distributions. Okay. Yeah. Okay, so let's start. So I want to now look at the random walk model, again to recall what the model is. So we had my time series now is just a location of a random walker. Okay. So, let's say I start at the origin, and I just make random independent jumps. I go up to n steps. So my sequence is updating by this Markov rule. So once again, this is the current position at step n, which is the previous position plus some noise. And these etas, they are IID variables, each drawn from some symmetric f eta. For simplicity, I'll assume symmetric. So that the mean position is always 0. Okay? And I want to know what's the distribution of the maximum. So x max as before. So notice in the IID variables it was the maximum of the etas, but here it's actually maximum of the positions themselves. Okay? And these positions, as we argued last time, that xn, xm was, if the sigma square is finite, was a minimum of n and m, and therefore it's a strongly correlated variables, okay, for m not equal to m. And if you put m equal to n, it's sigma square n, that's fine. So this is, so therefore this is strongly correlated, there's no finite correlation length. And we want to know how the maximum is distributed. Okay? So, as in the IID case, the most convenient thing always is to look at the cumulative distribution. So, okay, I won't call it x because x I want to keep it as my running variable, so I want to call it something, let's say a. So, this is the probability that this x max is less than equal to a up to n steps, right? That means, what's the probability x max is less than a? Now, as I said, x max, because it's the maximum of n IID variables, so this is the same as the probability that each of them is less than equal to a. Because if the maximum is less than a, each of them has to be less than a. So this means this is the event, this is the probability that the walker starting from x0 equal to 0, so here I put a condition x0 equal to 0. So this is the event I'm interested, because if I know the cumulative distribution by taking derivative with respect to a, I can get the PDF of x max. So what is this event? So this is the event that this random walker stays below the level A up to step n. Okay, so this is this survival probability. What's the probability that it does not cross the level? So this is the probability that the random walk trajectory Now, before I proceed, what I want to do is I want to just make a transformation to reduce this quantity, this observable, into something which in physicists are more familiar with. So for that, what I'll do is I will, this event here is the same as the probability that a minus x1 is bigger than 0, a minus x2 bigger than 0, a minus xn bigger than 0, right? Just rewriting this. So now if I call a new random walker, let's call it xn tilde, which is just a minus xn. So this event is the same as the probability that this x1 tilde is positive, x2 tilde is positive, xn tilde is capital N. And this xn tilde, xn satisfies this evolution equation, so therefore xn tilde is just again xn minus 1 tilde, and what is this? So x is okay, a minus x tilde and minus eta n. So this is a, basically you have moved your, reference origin from 0 to A, and you are looking at the walk from, downstairs basically. So the walk, if you put yourself here and look at this as your positive axis, walk starts at a distance A. This is your new origin. It starts at a distance A, and it stays above the origin, which is below, of course, in this picture, but when you look in the opposite way. So this is the probability that this path stays positive up to n steps. And this xn tilde is, because eta n has the same distribution as minus eta n, so therefore xn tilde is statistically same as xn. Okay, so this is exactly equivalent to probability I'm just making a shift in the origin basically. Given that initial position x0 was A. Okay? Just see from this point of view. You have shifted yourself to origin, and imagine that you just reflect this path around this. Okay? Then you see that when you reflect, you are starting at A, right? If this is your origin, you are starting at A, and then you are jumping, and basically you stay below this level. That means you stay above this level. Okay? So this is what is called persistence. So this means basically I have this time here. I have a random walker that's starting at say A, and it's doing jumps. And I'm kind of hardwall at the origin because I want only those trajectories which stay positive up to step n, starting at A. Okay? Is this clear to everybody? So it's just just reflecting because we physicists, we are used to think of the propagator this way. So instead of putting a barrier up there, you just look from the reference of the barrier, and then it's just a zero crossing problem. Okay? So this is just a probability that the walk stays positive. Okay? Starting at initial value x0 equal to A. Okay? So like we did for free propagator, so I'll define this object now. The Green's function, I put a plus here, and I use little n as some kind of running index, if you like, because you can use capital N or little n, same thing. Okay. So this means that I start at x0 and I arrive at x, some position x here, after step n. This is step n. So what is the probability that starting at x0, I arrive at x and this is the probability density, so it's this times dx arrives at x after n steps, and it stays positive in between, all through, without crossing the origin basically. So it's exactly this event basically. So this is, more generally, this is probability that the first guy should be positive, second guy should be positive, n-1th guy should be positive, and nth guy should be equal to x, little n, sorry, given that you started at x naught. So that's the definition of the restricted Green's function. So I'm looking for trajectories. See, earlier I was looking at all trajectories going from x naught to x. That was my gxx naught n, for which we could remember unrestricted Green's function or free Green's function. This was we had computed in the class. Okay. So at least there is an explicit expression for that. So now we want to find out a similar expression for the paths that stay positive, because if I know this, suppose I know this, and then this survival probability, this Q max of AN, is just G plus x naught n, sorry, n equal to capital N now, and x naught is A, I'm starting at it, and I have to integrate over the final position from 0 to infinity, right? Because this is this, if I integrate this from 0 to infinity, this is just the last guy is positive also. So that is exactly the probability that the walk stays positive up to step n. Just a final position, you just integrate from 0 to infinity. So this is exactly, so if I know this restricted Green's function, then this is exactly the survival probability, or equivalently the distribution of the x max, cumulative distribution of the x max. So if I can calculate this, then by taking the derivative of A, I can calculate this PDF of the x max. Okay, so that's the goal. Now, why is it a difficult problem? So just like we did for the free guy, if you remember, so I want to write down a recursion relation for this restricted propagator. Okay? And I can do either backward or forward Kolmogorov, backward Kolmogorov, recursion relation. So what is the recursion relation? Again, keep this trajectory picture in mind. So first I'll do the forward thing. So I started at x naught, and I'm arriving at x, staying positive up to n steps. So I look at where did I go after n minus 1 steps, starting at x naught. Okay. So this is my x prime here, just one step before. Suppose I arrived at x prime, and then I have to make a jump from x prime to x, and because again it's a Markov process, so they are just a product. But now the x prime is going from 0 to infinity, because this x prime here, it cannot cross, so it can take only value from 0 to infinity. Okay? And you started from the initial condition. Delta function of x minus x. So that's the problem, and similarly, the backward equation, where you just look at what happens in the first step. So suppose that first step, you move from x naught to x naught prime, and then after that you are looking for, so here I look at first step, x naught, I move to x naught prime. And then starting at x naught prime up to n minus 1 steps, I stay positive and reach x. And here I jumped from x naught to x naught prime. So this is my jump distribution. And again, this value after the first jump, the end value here, it can be anything from 0 to infinity. And again with the same initial condition. So I need to solve this G plus, and then do the integral over dx to get this, okay? But what is the problem? What's the difference between, they have exactly the same recursion relation, except that when it was free, for example, the forward equation for the free guy was minus infinity to plus infinity, g of x prime x0 n, and f of x minus x prime dx prime. Because the forward equation in this x prime, there's no restriction, it has to be stay positive. So it can be anywhere from minus infinity to plus infinity. Okay? So that's the only difference is that now my integral over x prime is going from 0 to infinity. But this is a big difference because it screws up the whole problem, and the problem is extremely hard. So this problem, so what is the problem? I mean, you might think that it still has a convolution structure, okay, in x. But it's not true because the convolution structure, you know, if you take Fourier transform, it was, remember, by taking Fourier transform, they are breaking into product of the two. But that convolution structure will hold only if the integral is from minus infinity to plus infinity. It will not work. Fourier transform does not work when you have a restricted space like this, okay? So this problem is very hard to solve, okay? So in general, when you have problems like this, so such things, and also you notice that, I mean, so you might say that, okay, forget the Fourier transform, what about the Laplace transform? Because the x is positive, so maybe Laplace transform will work. Unfortunately, it did not work. For the Laplace transform, the convolution structure to work, this should have been from 0 to x, okay? Then you could take Laplace transform on both sides and written as the product. But here you neither can use Fourier transform, nor you can use, so neither Fourier or Laplace will work. So such problems, when you have, you know, an integral equation or recursion relation if you like, but where the integral is not over the full space but over the restricted space, so there is a name for it. These are called Wiener-Hopf problems. They appear in many, many areas. They appear in, for example, photon absorption from the atmosphere when you look at the cosmic ray background. And they appear in nuclear physics. They appear in many, many different problems. So these problems of you know, radiation in finite space and so on, absorption of radiation. So these are called so there is a very nice paper. So Wiener, of course, is famous Wiener of Norbert Wiener is a mathematician, and Hopf was actually an engineer, mathematician also from Germany, and so they work quite a lot on this problem, and it's still, you know, I'll show you, you'll see in a minute, it's very hard to find the solution for general f of x. And then there's a very nice paper by a Russian guy called Vladimir Ivanov. He was an astrophysicist, and actually he had a very nice solution for this guy, okay? And this is, and it's published in Astrophysical Journal. And the difficulty is precisely this, because neither Fourier or Laplace will work. So how to, you know, how do you solve this problem? So there are special cases you can solve, okay? So for example, I mean, if I take a Laplace double exponential distribution, let's say something like this. Then you can find the solution of this integral equation, because you can actually, for this particular thing, you can reduce this integral equation to a differential equation, and then you can solve it. Still non-trivial, but you can still solve it, okay? I'll not do in the details, you can find in the book if you like. So this is a very nice distribution, because in many of these discrete problems, you know, you can use this as a benchmark, because for this you can actually exactly solve the problem, okay? But in general, I mean, so for such integral equations, and you know, usually in the physics language, this is called kernel, okay? So here, of course, the kernel has a particular this thing. It's a positive function, and it has this normalized. It is normalized to 1. Okay, and so generally, for general kernel, the solution is not known. But for the case of f of x minus x prime, so there is a very nice formula due to Ivanov. I'll just write the formula without proving it, but you will see from the formula how complicated it is. Okay. So the derivation is quite non-trivial. So it's not a form. I mean, the formula is for the. Okay. So you take this guy. So remember, x naught, and n, they're all positive. Okay. So I first take the generating function of this with respect to n, and then you take a Laplace transform with respect to x, final position, and then I take a Laplace transform with respect to the initial position, and I integrate over all final initial positions. So it's a function of 3 variables. We are looking at the 3 transforms, and this guy has a nice formula. So let me write down this. Where it's quite horrible, as you see. So you have given me the distribution f of eta, and I want to solve this integral equation. Okay. So first you look at the calculate the Fourier transform of f of eta, which is easy, and then you put it in this formula here. So this gives you phi of lambda s, and then this right hand side is phi of lambda s, phi of lambda 0 s divided by lambda plus lambda naught. Okay. So from this expression you already see is very, very, very complicated. Okay. So it's a very difficult problem. It's not an easy problem. Okay. So and even to extract the asymptotics behavior for large n from this formula is highly non-trivial. Okay. So this is discussed in detail in the book, but I just wanted to show you the solution just to show that you appreciate that is how hard it is to solve this problem, the distribution of the maximum, even for this simple correlated process, basically random walk. But there is one nice result from this you can derive, and I'll do that before we actually go into the maximum. So remember that our maximum distribution, probability that Qmax cumulative distribution AN was this G plus of x naught n integral, so this is A. So basically we have to solve for G plus of x naught n from this, put x naught equal to A, and calculate this object. Okay. And this picture we had, so I should not forget this. So I go from x naught to x without crossing the origin. That's the G plus of x naught. Okay. So, okay, since here, I mean, finally, I need to integrate over x, so let's do that. So if I integrate over x, okay, how do I do that? So I have to just set lambda equal to 0, right? So if I take lambda equal to 0 here, you might think that, okay, I just put lambda equal to 0, therefore this is 1. Not true, because when you put lambda equal to 0, this thing goes to 0, but when you put lambda equal to 0, this guy diverges. dk over k squared diverges as k equal to 0. So you have to calculate carefully the lambda going to 0 limit. Okay. And of course, what you see is that this G plus, of course, depends very crucially on this jump distribution, okay? So I want to look at the limit lambda goes to 0. So how to calculate that limit? So this usual trick is that you first make a change of variable. You call k equal to lambda times q, so that this guy comes out of this. So then you immediately see that this becomes lambda square, and there's a Jacobian lambda comes in. So lambda square cancels, and what you get is dq log, and k is lambda q, okay? And now this is exact, and now you can take lambda goes to 0 limit. Because lambda goes to 0 limit, f hat k is the Fourier transform. So that means at k equal to 0 is just integral fx dx, which we know is 1 because of normalization. Okay. So then what you have is exponential minus 1 over pi log. So this becomes independent of q. It just becomes log of 1 minus s. This goes to 1. And what you have is integral dq over q square plus 1. But this integral is pi by 2. So pi cancels, so what you get half log 1 minus s. So this is exactly 1 over square root of 1 minus s. Okay, so lambda goes to 0 limit of this function is just simply 1 over square root of 1 minus s. Okay. All right, so let's take this now, lambda goes to 0 limit on both sides. So what you have is g plus of, maybe I should do it on the other side. And remember, this is the object we want from the. So lambda goes to 0 limit. So phi of 0s is 1 over square root of 1 minus s. Okay. So this means and this is exactly our object that we want to know, that is the Q max of AN. A is x naught basically. So when you integrate over x, so this is final point. So this is just the survival probability. What is the probability that starting at x naught, it does not cross the origin up to step n? Okay. So it's still quite complicated, even if you have integrated out the final position. Now, this, there's a name. So this was actually derived even before Ivanov. This is called the Polabchek-Spitzer formula. Okay. And so this is the distribution of the maximum, if you like, cumulative distribution of the maximum. The probability that the maximum value is less than equal to x naught, which is the same as the survival probability of the work starting at x naught. And its generating function and Laplace transform with respect to the argument. So this is given by this formula. So this is a, if you like, this is the, exact formula, but it's almost practically useless. I mean, because, from this to derive anything is very difficult. Okay. So, but there is one nice consequence of this Pollaczyk-Spitzer formula. So here you see from this that it explicitly depends on this jump distribution f hat k through this phi lambda s function, right? Because here phi of lambda 0s. So it does depend on this distribution depends on the noise distribution, and but we are always, as I said, we are always looking for universality, right? So one beautiful, amazing thing that we'll see immediately. Now suppose that you say, I want to just calculate the survival probability when you start at the origin, x not equal to 0, right? So this is the probability of this event given that you started at the origin. Because it's a discrete random walk, so even if you start at the origin, you're not going to cross immediately. You can jump this way and survive still. So it's a finite number. What is this number? How do I calculate this from this formula? So to extract the Q0n, and this is the usual, asymptotic analysis. So what you do, you make a change of variable. You call this as this integral here. You just call it z. So once I make this change of variable, then this will be Q max of z over lambda naught n s to the power n, sum over n from 0 to infinity, e to the power minus z dz, 0 to infinity, and then 1 over lambda naught, left hand side. So this is equal to phi lambda naught s by lambda naught square root of 1 minus s. So this lambda naught 1 over lambda naught cancels. So this is exact. I mean, I have not done anything, just made a change of variable. And now you take lambda naught goes to infinity, because if keeping z fixed. So if I take lambda naught goes to infinity, this argument goes to 0. So that gives me Q max of 0n. Okay. So therefore, Q max or Q, I call it Q max. So if I start at the origin, okay. So this is, you have to take the lambda naught going to infinity limit of this. Now, phi lambda is defined like this. So when you take the lambda naught goes to infinity, you see that this guy is just lambda naught square, and so lambda naught 1 lambda naught cancels, and you get e to the power minus 1 over lambda naught times something, which is finite. So lambda naught goes to infinity limit, this whole thing goes to 0, and this object here just goes to 1. So you have an amazing answer. Whole dependence on the noise distribution has just dropped out, gone out of the air. Right? So this is a totally universal result. That means if I take any random walk, whatever be the jump distribution, as long as, okay, I mean, I forgot to say that one assumption here is that the f eta has to be symmetric and continuous. I mean, it's PDF, I mean, cumulative distribution is continuous. So for example, exponential, Gaussian, uniform, all of, not lattice random walk, which has a discrete jump, but otherwise any other distribution you can think of, so that is allowed. And for all such distributions, if I start at the origin, then this guy is completely universal, okay? And you can easily, so you just have to expand this right hand side in powers of s and compare the coefficients. So you get then this very beautiful result. Which says this is universal. Note that I have not assumed it's large n. It's true for any n. So It's a very rare result. That is universal for any n. Universal in the sense does not depend on the jump distribution. As long as a theta is symmetric and continuous. So I can take uniform, exponential, or Gaussian, whatever. You just do this. You can do this on your computer in 2 minutes. You can do it. Suppose you start at the origin. You draw a random number from this distribution. Let's say uniform distribution. Then again you draw, and you ask what's the probability. Let's say up to 3 steps, it remains positive. Okay. You can see n equal to 1. N equal to 1, of course, trivially, probability that it stays positive is just half because it's symmetric distribution. So it has to jump on the positive side. Probability is half. But n equal to 2, it's already non-trivial. So you first one, you draw two random numbers, and you ask, what is the probability that both x1 and x2 are positive? And you do it for Gaussian, you do it for exponential, and amazingly at the end of n equal to 2, if you put n equal to 2, this answer is, what is it? N equal to 4C2, that's 6 times 2 to the power minus 4. So that's 3 over 8. So you can repeat these things. It just takes 1 second to do on your laptop, right? Just do it for, Gaussian and do it for exponential, do it for uniform. For all of them, we'll get the answer at 3 by 8 for n equal to 2. And for general n, this is the answer. Okay. So this has a name. This is called the Spar-Anderson theorem. This is a very famous theorem, and we'll probably use it later when I talk about record statistics. So this is one guy, not two guys. Spar-Anderson is just one name. It's a Swedish mathematician. So he derived this result in 1954. So he used very combinatorial methods, and he derived this result. And then people thought, oh, this looks very simple. It looks like a binomial distribution. Some 2 to the power minus 2, and it looks very simple. So it must be trivial to derive. And then people tried, and each time somebody tried to derive this result, their paper turned out to be much longer than the original Spar-Anderson paper. And this includes, people quite famous, Uriel Frisch, you probably know, he has visited Bangalore many times. He's a turbulence guy. So he and his wife, they also tried to prove it. In fact, his paper he says that our main goal was to derive this result in 2 minutes, but we spent 2 years to derive this result. So it's a very non-trivial, it looks very simple, okay? But it's a very, very, very non-trivial result. I will show you proof later if I have time, which is a relatively simple proof. But this is a very beautiful theorem and very beautiful result for this. So this means Qmax 0n in the survival probability language, it's the probability that you start at the origin, and what's the probability you stay up to step n. And in the language of maximum, this is the probability that if you start at the origin, what's the probability that the maximum is less than equal to 0, right? So maximum is less than equal to 0 means that basically the walk has to, maximum is just this guy itself, the starting point. So that means this is the walk stays below 0 up to step n. And because of the symmetry, this is exactly this. So Qmax, so this says that, the probability that the maximum takes the value 0. So this is exactly the probability that the maximum is 0, essentially, okay? It can happen because if you jump always on the negative side, then you stay below 0 all the time, right? So therefore, all this example, maximum itself is 0, okay? And that value, that means, just exactly at one point, the value of the PDF, if you like, or CDF, or whatever it is. So this is exactly universal, okay, for any n, and this is what is called the Spar-Anderson theorem. Okay. And the proof, again, original Spar-Anderson didn't go through this proof. Here I started with the Ivanov formula because this is the formula that we used quite a lot for many, many different applications. I'll not go into the details of those, but this is a formula which is very general formula, general Green's function. And so therefore you can, starting from this formula, you can derive many of these results. Both Polazek-Spitzer and Spar-Anderson are special cases of this formula. Okay? So this is the key formula. And but if you want to calculate, for example, the distribution, what is the probability distribution of the maximum from this, or from this formula here, this guy, you see that you cannot invert this Laplace transform, right? Because it's a very complicated function. So it's impossible to exactly invert this Laplace transform. You can do it for special distribution like this Laplace, like this double exponential distribution, but not in general. So deriving the, the asymptotic behavior or scaling function of this is not easy from this formula, okay? But we'll be able to do something in one limit, which is this Brownian limit, that continuous time limit that I mentioned in my previous lecture. We said that the random walk, when this sigma squared, the variance of the eta noise is finite, then in the long time limit, the random walk converges to Brownian motion. And so for Brownian motion, this recursion relation that we wrote down here, remember, that this will be just G plus, will be exactly same equation. So I'm asking, I have a Brownian motion, so this is 0 and I start at x naught, and I have a Brownian motion in continuous time, and I'm asking what is the probability that it arrives at x starting at x naught and that it stays positive up to time t. So that's G plus of, exactly analogous, G plus of x naught t. And that satisfies, exactly just with, as we did in the continuous time in the free case. You just, do a Taylor expansion and you arrive at this equation. But now this equation has to be solved only in the upper half plane, right, x positive. And with the boundary condition that G plus at x equal to 0, starting from x naught up to any time t is 0. Because you don't want the particle to cross the origin. So the probability that it will arrive here, if it arrives here, Brownian motion, it will cross immediately. So you don't want it to arrive here. And so you have to impose this boundary condition. So you solve in the upper half plane this partial differential equation with this absorbing boundary condition. So this absorbing boundary condition tells you that it basically what it does, out of all possible trajectories, it selects only those that stay positive up to time t, okay? And this equation, as we'll see in the next lecture, tomorrow's lecture, that this actually you can solve it quite simply, and that gives access to this distribution, because you know this, so just integrating over final x, I can derive the full distribution of x naught n in the continuum limit. But this is for a subclass of jump distributions where the sigma square is finite. So that means where the central limit theorem holds and Brownian and random walk converges to Brownian motion. So in that case, we'll be able to compute exactly the distribution of the maximum. But for general, jump distribution with finite n, we can only calculate this kind of Laplace transform of it, but we don't know how to invert this Laplace transform. So in physics, actually, often is the inversion of Fourier and Laplace transform which are the most difficult parts. And many interesting physics are hidden inside this. So that's the status of this problem. So you see, even for simple random walk problem, the EVS, extreme value statistics, is quite a hard problem to solve, mathematically. And but what I'll do tomorrow is to solve in detail the Brownian motion limit, and we'll see what the exactly scaling distribution is, and we'll see that it's very different from the Gumbel, Fresher, and Weigel. And once we do that, then after that I'll move to other observables. Okay. So I think we'll stop here. Yeah, if you have any question, please ask. Don't hesitate to ask question, please. So the point is not to rush through the thing. I want to explain everything as clearly as possible. So please ask questions. Yeah. So directly you cannot take Laplace transform in this equation. Right. So that's why I'm saying the derivation of this is very, very different. It's really quite complicated. It turns out at some point you have to take a Laplace transform, not directly on this equation. So you have to, you can actually write down. I don't want to get into details. It's quite complicated derivation actually.
So if I think of defining a new function g, let's say, which is the inside step function times f.
Yeah.
And then convert the limit to 0 to.
No, it doesn't work.
It doesn't work.
No, because the function has to be continuous. You cannot do discrete things. That's the problem with the Wiener function. In fact, Wiener problem, if you, so what the Wiener, if you open any mathematical physics books, like Courant-Hilbert or any other book. And you will see that the Wiener-Hopf problems is a special chapter there, okay. And they solve this, what they do is they take this generating function, and then it becomes precisely, to try to do this theta function thing. But then because of you cannot analytically continue in the complex Z plane, and it becomes a mess, basically. So nobody knows in general how to solve Wiener-Hopf problems in general. Okay. So it's quite remarkable. So in general, I mean, this equation here, if I give you f as an arbitrary function, okay. So if you look at Courant-Hilbert, I mean, they'll call it as a kernel basically. Okay. So if this kernel is arbitrary function, need not be positive or normalized to unity. So in that case, nobody knows what the solution is. Okay. It's a still unsolved problem. But for this special case, when you can interpret this as a probability density function, which means it has to be positive and normalizable to unity. So in that case, this is the solution. In fact, this solution, Ivanov solution was not very well known in the mathematics literature. Nobody knew about that. People knew about Polar-Jake-Spitzer, which was a special case of that. But Ivanov formula is actually a physicist formula. I mean, it was, as I said, he was an astrophysicist. He's still alive, actually. He lives in Dubna. And he was quite happy to see that we use his formula quite often. I mean, he actually wrote an email to me once, and he was a very nice person. So, and his actual derivation is very, very hard. So, for example, I mean, here is another unsolved problem. If I ask you, so this is the probability that it stays positive, right? So I ask you, okay, take the same random walk problem, but now, so I take again exactly same random walk problem. Sorry, eta n. And I start at x naught, and I ask what is the probability that you walk up to n, after n steps, it arrives at x, but staying inside 0 to L in a box. It doesn't leave the, in fact, this problem appears in this photon problem. I was saying photon absorption problem, because you have a slab and you want to absorb the photons there. So there, this is exactly this problem that you want to calculate. So this is the Green's function of going from x naught to x, but without leaving this box 0 to L. So that means here you just have 0 to L. And this, even with a normalized fx, it's an unsolved problem. Nobody knows how to solve it. So Ivanov actually in his paper, at the end he says that, okay, I think I have found a solution. So I actually asked him if he has this solution, because we actually came across this problem in Mini-Detment. Take for example this as a Gaussian distribution. So this integral equation, nobody knows how to solve. Yeah, except for this, that's why I said, this is a very special distribution for which, you can actually reduce this integral equation. Let me, maybe if I have 5 minutes, I can show you how to do that, okay? So why this is a very special distribution? Because, okay, you see, if I have f eta equal to half e to the power minus eta, right? So this is a nice trick. So if I take a derivative, so this will be half. So derivative of dd eta of mod eta. Mod eta means it's plus eta and for eta positive and minus eta for eta negative. So if I do this, so then this will be just sine function of eta. Right? If eta is positive, is plus 1. If it is negative, minus 1. Okay, so you have sine, but sine function is, you can write down as 2 times theta function of eta minus 1. Minus sign here. Okay. Right. And now you take a second derivative. So what's the second derivative? So you have minus half times sine eta, if you like. Okay, let me write it as sine eta. So sine eta, and if I take a derivative with respect to this, I get a minus sine eta times e to the power minus eta minus half, and derivative of sine eta is 2 times delta function. What's the point of all this? Because sine eta, when you is just 1, right? So what you have is half times e to the power minus mod eta, that's first term, minus delta function of eta. So if double prime eta for this particular case, it actually satisfies a very nice equation. Because this is f eta. Okay? So now we'll see the magic. So I take this guy, I take a second derivative with respect to x. So this doesn't depend on x, right? So this is as before. This is x naught n. But for this guy, I'm just going to use this equation, because f double prime of x is just minus delta x minus x prime plus f of x minus x prime. Right? So for the first term, see, this is delta function integral, so x prime just becomes x. But the second term, I use exactly the same recursion relation again. So this is just g plus of x naught n. So you have now a differential equation instead of integral equation. And now you can take a generating function with respect to n, and you can actually solve this equation quite easily. Okay. So this trick actually works for this particular distribution. And so many of these integral equations, this is a very useful trick actually, because this you can then benchmark, as even if you cannot calculate exactly, you know how the function will behave. So this has played a very important role in that sense in this distribution. Okay. But generally, it's an open problem. I mean, nobody knows how this maximum, this Green's function inside a box or even a semi-infinite system is totally open problem. Okay? So tomorrow is what time? Morning. Tomorrow is Thursday, yes, that's true.